Welcome to this video. I'm going to show you how to work with force time graphs and how to find the net impulse and momentum change from the graph. Here's our problem. A car is speeding up and slowing down. The net force on the car changes as time passes. Find the net impulse on the car using the graph provided, this graph. Okay, what do we have here? There's a trick to using these graphs. You might guess maybe the trick is slope. Use the slope of the graph to answer the question. Well, as it turns out, slope is rise over run, change in y over change in x, and delta f net divided by delta t doesn't equal anything. It's not the acceleration, it's not the change in momentum, it's not the net impulse. It's not anything. So slope is useless to us. Let me erase that. There's something else we can use, which is the area under the curve. And this is our first exposure to area under the curve. I'll show you how this works. And let me tell you what the area under the curve equals. The net impulse for this particular graph, for a net force time graph. And that's really handy. Pretty cool. We're going to see that area under the curve equals net impulse by the units. So let's get to it. I'm going to take this away. And I'm putting this up, but now I'm taking it away. Okay. Remember our task, should we choose to accept it. Find the area, find the net impulse. First step, I'm going to take this graph that you see on the page, the blue line, and I'm going to divvy it up into normal geometric shapes. So the first thing I can do is I can draw a line right here down to 2. And hey, I just made a triangle, which is a shape, a normal shape. The next thing I'm going to do is draw a line from here down to 3. Let me try a little bit better. Like that. Well, you get the idea. There it is. A perfectly straight line. Okay, why did I do that? Because now I've just formed a rectangle and a triangle, 2 more regular shapes. And the last line I'm going to draw to form one final regular shape is that right there. And boom, just like that, I have another triangle. Let's call these area 1. Let me use purple to show my work. Area 1, area 2, area 3, and the last triangle is 4. Okay, we have to find the total area under the curve. The way we do it is by finding the area of each regular shape and adding them all up like the equation above shows. Alright, this is not too tough. How do we find the area 1? It's a triangle, so the area formula is half of base times height. What's the base of triangle 1? Well, triangle 1 goes from 0 seconds all the way over to 2 seconds. So how much does it span? What's the base? The base is 2 seconds long. The height is from 0 all the way up to 5 newtons. And if you read over like that, goes over to 5. So the height is, oh gosh, the height is 5 newtons. That's how tall my triangle is. Right, let me get rid of that, keep things neat. Next, I have area 2. Area 2, folks, is a rectangle. Oh, I didn't calculate area 1. This comes out to 5 Newton seconds. Hey, 5 Newton seconds. That's the unit of impulse. So maybe you're starting to believe me. Maybe you're starting to believe that the total area is equal to the net impulse, because the units seem that way. Okay, so now you're starting to believe me. You're like, alright, this guy's not just some, some who's a what's it, lying about graphs. Anyway, where were we? Okay, on to the next part. We have to find the area of shape 2. That's a rectangle. Rectangle has area equal to base times height. What's the base of the rectangle? Well, it goes from 2 to 3 seconds. So that spans a time of 1 second as the base. The height is from 0 up to 5 newtons. So the height is 5 newtons. And I multiply these together to get 5 newton seconds. Area 3. Area 3 is what is that? A triangle. So the formula is 1/2 base height. That's how you find the area. And I'm going to run out of room. 1/2 base height. The base goes from 3 to 4. So total, the base spans 1 second. So let me put in 1 second. And the height is the same as what I drew already. It's from 0 to 5. The height is 5 newtons. Change my color. 5 newtons. And overall, that gives me 2.5 newton seconds. Now on to area 4. And I'm out of room, so let me do it down here. Area 4. This is curious. It's a triangle. That's not curious. Triangles have the formula 1/2 base height for their area. The base is easy. It goes from 4 seconds to 5 seconds. So this triangle spans a total of 1 second from 4 to 5. And what about the height? Well, notice that it doesn't go up. The line, the triangle, is not going up into the positive half of the graph. It's going down into the negative half. So the height is from 0 down to what is it down to? Down to 2 newtons. And the height then is not 2, but negative 2 newtons. So you multiply this out and we get negative 1 newton seconds. So check that out. If the line, like this, see this blue line right here, well, now it's red. If it goes below the x-axis, here's the x-axis right here, and if the line goes below the x-axis, you get negative area. So if your geometry teacher ever told you that you can't have negative area, well, they were technically right. They were right. But we use negative area on these graphs. So if you want to go back, send them an email, say, hey, that's not right. Then I give you permission. The last thing that we have to do is add up all of these together. And I've shown that work here. The total, we find the total by adding up area 1 plus area 2 plus area 3 plus area 4. There's the work, and this comes to 11.5 newton seconds. And yes, that is the net impulse. The area under the curve, when you add up all of those areas, once you find the answer, you instantly know the net impulse. And because net impulse equals change in momentum, you also instantly know the value of momentum change. So that's how you solve these problems.